Welcome. My name is Rebecca Gorelli. I am the K-12 Science and STEM Specialist here at the Department of Education. Welcome, everybody. Hopefully you are in the correct webinar. This is the 5E Instructional Model and Science Notebook. Here's our goals for today. The first one, understand how using Science Notebook directly correlates to three-dimensional instruction in the new Arizona Science Standards. Secondly, discuss the rationale of using Science Notebooks as a learning tool. We're going to deepen our understanding of the 5E instructional model. And finally, take that 5E and relate it to how do I actually transfer those components of the 5E into a Science Notebook. So we're going to talk about how to organize a notebook. So let's start with our first goal. And we're going to dive into three-dimensional instruction and the new Arizona Science Standards first. So here's a document that I did provide for you in the materials you could have previewed. So hopefully you've seen it. If not, that's okay. I'm going to blow it up here in just a second. This is from the National Research Council, and it describes the new vision for science education by really laying out what will science education involve less of and what will it involve more of. So I'm going to blow it up here, and if you don't mind, just take a minute and review it and think about 3 to 5 items that resonate with you, talking about these instructional shifts. Okay, so thanks to those who participated, and we are going to go over this in just a second, but I do see some connections here with, a higher scale of blooms, students really doing most of the work, the teacher stepping back as the facilitator and guiding students, but really the students are doing the heavy lifting here in our new shifts with our new science standards. So let's take a look at this word cloud. This was generated with a group of high school teachers in Coolidge, and basically we're asked the same questions, and here is the input. So on the left you can see what should a science classroom see less of, and we're talking about rote memorization, worksheets, textbooks, pre-planned outcomes, one right answers, really just that cookbook sort of one and done sort of labs. Those are done now. So what we're going to move towards on the right here is students being engaged, investigating, modeling, explaining, exploring, arguing from evidence, and it's really driven by students. So what's really wonderful about our new standards is that we're really making this huge instructional shift from learning about to actually figuring out, and the students are going to be in that driver's seat. And so let's just gain a little background information to how our standards were actually created. These two documents represent the research that was used to develop our standards. And if you know a little bit about the next generation science standards, they were also built using this same framework for science education. However, Arizona also used this framework, and so there are some similarities between the next generation science standards and Arizona science standards, but they are not the same, because in Arizona, we also used an additional research document to develop our standards called Working with Big Ideas of Science Education. So when we think of NGSS, we are not a NGSS state, but we are a framework-based state because we did use the framework for K-12 science education to develop our standards. And so within that framework is something called three-dimensional science instruction. And so just take a look at this graphic. And we'll start with the first dimension, which is the science and engineering practices. These practices really describe the behaviors that scientists engage in as they investigate and they build models and theories about the natural world. It also includes the key set of engineering practices that engineers use as they design and build models and systems. The framework uses the term practices instead of a term like skills to emphasize that engaging in scientific investigation requires not only skill, but also knowledge that is specific to each of these practices. And there are 8 of these science and engineering practices. The second dimension is called the cross-cutting concepts, and these are not taught in isolation, but rather in the context within instruction. There are 7 of these. And finally, in the center, we have the core ideas. These have the power to focus K-12 science curriculum, instruction, and assessments on the most important aspects of science. These are physical, earth, and space, and life sciences. It also includes the using science, which is using science and engineering in the everyday world. These core ideas are also built in a coherent progression of learning for students from kindergarten all the way through 12th grade. So in the next slide, we're going to take a look at a video. This is about a 6-minute video that's really going to help us have a foundational understanding of what is three-dimensional instruction, because we really need this understanding in order to understand how do we transfer these 3 dimensions into a physical notebook. And so for our next live chat opportunity, while you're watching this video, I'd like you to think about these 2 questions. How do the Arizona Science Standards represent a shift in science education? And what did you see the students and teacher doing that could be put into a science notebook? So give me a moment and I'll pull up the video.
Okay.
It's 1.2.
When we learn things, it isn't for memorizing a piece of information. Just reciting science facts or principles is not what we want children to be able to do. We want them to be able to go out in the world and make sense of novel phenomena. So making sense of things really is engaging in a performance and saying, I need to construct an explanation of why or how this occurs. Okay, let's get started.
Are you ready? 56.
Throughout the 2 days, I want you to engage as the scientist, you as the student, you as the learner.
If it was room temperature water, would it be behaving in the same way?
What's the science behind this? What's happening?
As teachers start focusing on the next generation science standards, they will be able to help students see science as it really is, that it's not just a set of steps and procedures.
The real hope is that they can make a connection between what we do in the modeling of performances of science and what they do in their classroom.
Oh, wow. In this day and age, one of the factors influencing the next generation science standards is the globalization, understanding we're in a global community. We're not kind of an isolated entity here.
The next generation science standards takes the vision from the framework for K-12 science education and puts it into a set of performance expectations. And it calls for the students to actively engage in science. It sets out parameters for science education, clear goals, along with describing the 3 dimensions that students can engage in to make sense of science. 3 dimensions are the cross-cutting concepts, the science and engineering practices, and the disciplinary core ideas.
Most of those ideas are not new. The integration of them, pulling those 3 dimensions together, is new.
If we're going to have the kids doing that, instruction has to reflect that.
What I'm walking away from today, kind of a big shift for me, is we can focus in on something very specific to help teach a much broader, bigger idea, that it actually helps the students be able to do that application to new scenarios, new situations.
Cross-cutting concepts. There's 7 of them. The way we've organized them is around causality, structure and function, systems, scale and proportion, change and stability, matter and energy, and then the last thing, pattern. These cross-cutting concepts are tools that you provide to the children, and they use those tools to make sense of phenomena.
So we're looking for changes in the system.
There's condensation on the outside.
The cross-cutting concepts are a way of organizing the phenomena in terms of what the system is that's being studied. What did you define as your system?
We included in our system also the surrounding air.
The idea that there's a cause-effect relationship.
What's causing the cloudiness?
That's causing the bubbles to come off of the ice.
It's going to get pushed in the direction of the wind, right?
And finally, patterns used as evidence to support their explanations.
So to me, the pattern is just the fluttering back and forth, right? Do you have a question in mind?
Why that pattern, that
The back and forth
pattern?
What if we change the direction of the flag, if we turn it this way?
Okay. I want to go inside and make a little paper flag that we can blow on and manipulate.
The practices are a set of things that children do in engaging in science performances. Asking questions right here, that's what students do. As a professional teacher, you have to create an environment in which students are asking questions that help them make sense of things.
Ready?
150.
Why doesn't that ball return to that exact same level that you dropped it?
Engaging students in the practices really does pique their curiosity, and it helps them have a desire to go out and have more questions about the world, which asking questions is a practice. So it's something we want them to be able to do, to be able to discover more about the world.
What else contributes to it not reaching its maximum height that it started at?
The pull of gravity. Gravity is still pulling it back down even though it's bouncing up.
As learners, using evidence and using that evidence to construct explanations is important. I think having those experiences will really help students own the content.
More bounce, more energy in the bounce, and that's really the kinetic energy.
The last dimension of the core ideas, and there's nothing new here. We don't want kids at the end of instruction to recite the core ideas. We want them to use them in science performances, to make sense of novel phenomena, applying them to construct explanations and develop arguments.
So the alcohol is less dense than the ice. You can see the density in there is different.
Oh, yeah.
The core ideas in particular become valuable because we revisit them through every grade band, and they're moving forward in a very logical way. Those things we're asking them to do can be applied to more than just alcohol and water. It can be applied to cloud formation. It can be applied to condensation.
Why? What's happening?
I think what's exciting about the next generation science standards is this intersection of the 3 dimensions, and that we're not just working on practices one day. You really are infusing the 3 dimensions within the classroom.
One of the things that you've done is ask what if. By doing that, I have to be able to take what I know, what I've learned, looking at the models, looking at patterns, and applying them somehow to show that I understand what would happen if I changed a dynamic.
It's been real helpful to remember that, I can't do one without thinking about the other.
No change, we should add that, right?
That's how students are going to be thinking about them as well.
It's cute.
It's my hope that this will be the reform in science education that not only gets students more proficient in science, but builds interest in science.
Thank you to those who responded. I see something about the new standards require more rigorous thinking and making sense of things. Absolutely. Students they're documenting their experience and findings. They can put in their investigational findings. Absolutely. All right, so if you have some more ideas, feel free to drop them in the chat. I'm just going to keep moving forward here. So now that we have a foundational understanding of the 3 dimensions, let's move in to the rationale of using science notebooks as a learning tool. And so there's this fabulous book that you can see here called Science Notebooks, Writing About Inquiry. And in this text, it really describes the semantics behind using the term journal versus log versus notebooks. So I thought it would be a good place to start by just discussing the semantics and really thinking about what is the difference between a journal, a log, and a notebook. So journals are normally used or often used after an investigation. Okay, kids, get out your journals and reflect upon what happened. A log is something students might have a data log during an investigation to track, their thinking or collect data. A notebook is what is used before, during, and after the investigation. And so there's some real differences here, and I want to talk about them real quickly. First, the journal is really, where the kids think of reflecting on a lesson. And it usually starts something like, today in science, I learned, or I thought, or I was confused by. A log is usually where we keep data over time, and a notebook, however, can be something where we really keep all of our plans, all of our questions, our data, our thoughts, our pictures, analysis, explanations. So when you really look side by side at these 3, where we're really going to focus on today is how do we use a notebook every single day in class with our students? And so let's talk about why do we use science notebook? What does research say about science notebooks? Well, for students, it helps them gain ownership over their thinking. It's really an authentic learning tool. It helps them organize their ideas, and it reveals their thinking. It helps make that thinking visible by asking them to commit to their thinking on paper. It helps them reflect on and reference prior learning experiences. So if we're using the notebook every single day, I could say, hey guys, let's turn back a couple pages and let's really look at what we did on that day and use it to help push our thinking. Can used as a resource when speaking with their peers. So let's say we do a Socratic seminar or some other sort of student discourse engagement activity where they have all of their evidence ready to go and they can have confidence to speak to the evidence when making a claim. And the main reason we really want to use science notebooks is because we have these 8 science and engineering practices, and we want to really teach our students to act as scientists and engineers. And so within those practices, this is where they can analyze and interpret data, they can construct explanations and argue from evidence, and they can draw their initial models, make their thinking visible, then come back to the model and revise it, and then talk to their group and even the whole class to come to what's called a consensus model, where we draw everybody's ideas together. And on the teacher side of things, it's a really great tool for teachers to use for both formative and summative assessments. It can help support differentiation, support literacy skills, and it can help support teacher collaboration and refinement of practice, because if all teachers can get together and bring their students samples of their notebooks, it really makes that conversation much more rich. And finally, it is an excellent planning tool, and I'm going to show you how to use it as a planning tool in just a second. And so that's really why do we use science notebooks? So let's move on and just really focus on the science and engineering practices, because these are the things that students are doing. This is the dimension that really has the students engaged in the work and really tracking their thinking and making their thinking visible. And so let's just look at them. We're asking questions and defining problems. The yellow is for science, the green is for engineering. Number 2, develop and use models. 3, planning and carrying out investigations, analyze and interpret data, using mathematics, constructing explanations, engaging in argument, and obtaining, evaluating, and communicating information. If you really look at these 8, can you think of how many different ways a student can engage in this practice while working inside of a notebook? And that's what we're really going to break down as we move forward here in this webinar, is really how do we get these science and engineering practices to be placed in a notebook? And so let's do a little reflecting of our own practice before we dive a little bit deeper. And this is a table that I took from an article by the authors who wrote that fabulous book I just showed you. And I will provide the article for you as a resource when I provide a follow-up email. But let's just take a look at this. What I like about this is it breaks down where is an educator at this point in time. So we have the novice category. Then if you move to the right, you have developing. And if you continue, you have experience. So what I want you to think about right now before we move on is just read this table over and think, where are you at right now at this point in time? Are you a novice? Are you developing? Or are you experienced? And all levels of experience are welcome. So go ahead and in the chat box, just kind of think about where are you at, and let's have a little collaboration in the chat box. Okay, so we have a couple different levels here. Okay. Thanks to those who participated. If you still have a thought, go ahead and drop it in the chat box. We're going to move forward. So our next goal is to really dive into the 5E instructional model first, and then we're going to take that 5E model, we're going to break it apart, and we're going to talk about what could be put in the notebook to really represent that 5E model and our 3-dimensional instruction. And so let's just do a little more reflecting. Where are you guys at in terms of your comfort level with the 5E model? So in the chat box, if you could just place a number 1, 2, 3, or 4. So I have kind of a baseline data of who is with me today. All right, so let's move on. And what I have for you this time is a short video. It's about 5 minutes long, and it really goes through each of the 5 E's. So just to give you a heads up, I am going to skip past the first 45 seconds of the video, and then I'll start it. And while you're watching, what I'd like you to think about is what aspects of this instructional model might you already be doing with students. This might not be entirely new. There may be components that you already use in your classroom. So just really think about that as the video goes on.
A very approachable model for teaching inquiry science is the 5E model. This approach was developed and refined by BSCS in Colorado, and it's based on a number of different learning cycle approaches. The nice thing about using the 5E model is that it follows the natural way that we solve problems in everyday life. First, there's a period of initial curiosity or engagement when we begin to wonder what might be happening. Next, we explore related ideas and we try to gather more information about what has piqued our curiosity. Then, after we have some information, we develop an explanation. Sometimes we even take that explanation and extend it to other situations. And finally, through use, we evaluate the quality of our explanation. So this is an everyday problem-solving strategy, but it's also very similar to what scientists do, and it makes a nice model for teaching science. So to look a little more closely, in the classroom, the engage phase allows students to connect what they already know with a question or an idea that's just been presented with them. Hopefully, it will generate some curiosity and desire to learn more. The engage phase also helps a teacher understand how much students know or don't know, and even more importantly for instruction, to figure out what their misconceptions might be about the idea. So if you were going to be starting a 5E model lesson or a 5E unit, you might ask a question, show something interesting, or pose a problem to your students. It's also important to think about the 5E model as something that can be used for just a single lesson, or that can occur in stages over multiple lessons over several weeks. The next step in the 5E model is the explore phase. This is where students have one or more real experiences with physical materials. It allows them to do experiments, collect data, make observations, make connections, and ask questions. It's an important phase for creative thinking and skills development, and it's usually carried out by students working in groups. In these situations, the teacher has an opportunity to act as a coach or facilitators while students actually do the investigations. The next component of the 5E model would be the explain phase. This is where students begin to make sense of their data. They describe their observations, and based on what they've been able to collect, they come up with explanations. They also listen critically to others' explanations, and sometimes even have opportunities to defend their own rationale. It's a wonderful opportunity for students to develop science vocabulary, to use it appropriately in context, and to learn to apply and interpret evidence. In these cases, the teacher is guiding student reasoning, asking appropriate questions, and directing students to other resources that can help further their learning. Finally, in the 5E model, students use the information that they've gained to propose solutions and extend their learning to new situations. This is the elaborate phase. The teacher helps students broaden their understandings during this phase and extend their ideas to other situations so that they can draw much broader conclusions than what they found originally with their investigation or experiment. And finally, everyone involved evaluates. This is the last phase of the 5 model. Students have opportunities to demonstrate that they've learned a skill or a concept. And not only are they evaluated perhaps by their teacher, they also have opportunities to judge and evaluate their own progress. Similarly, teachers can evaluate students, but also their own progress. And if need be, they can examine alternate strategies for assessment. So I'm certain that all of us have been in situations where we find that after a lesson, it's important to go back and adjust misconceptions or help students focus on new information that's come to light that will help them understand the lesson in greater depth. So what might this look like? If we pick a very simple example from physical science, we could start with an engage phase in which you might ask students, why does ice, which is a solid, float in water? It seems counterintuitive because most students' experiences are with solids that will sink, particularly in the case of heavy solids such as metals. Students could explore this quite simply by comparing the mass or weight of equal volumes of ice and water. They would then discover, of course, that water, liquid water, has a greater mass than the same volume of solid water or ice. This would come in the explain phase, and it would provide a wonderful opportunity in context to explore ideas related to density. In the elaborate phase, students might investigate the densities of other materials and learn about the structures of ice, a solid, which is a crystal, and liquid water. And finally, students would write about or report on their findings in groups, or create group concept maps to represent their findings. So again, a very simple idea, but yet it could go through the 5E model.
Okay, so hopefully that gave you some background on the 5Es, and it looks like a few of us are already doing some of the 5Es. So let's break it down a little bit further. Here's a document that BSCS, the creators of the 5E model, put out, and I will provide this for you in a follow-up email. So what I'd like you to do is just really scan through the summary and read the summary of each of the 5Es and just think, what is the key feature of each of these? So I'm just going to give you a minute of think time, and then I'll go over it with you. Okay, so hopefully you had a moment to just kind of read through each of the summaries. And so what I notice about the engage that relates to our standards and three-dimensional instruction is this is really where we engage our students with phenomena, which is just an observable event that happens in the real world that we can start to figure out. And so this is the part of engage. We can activate prior knowledge, we can look at misconceptions, and engage them with the phenomena that they are going to explore. When you get to the explore phase, this is where students start to engage in the science and engineering practices. And one of the best ways to go from phenomena to explore is by really asking students to generate questions. What are their questions around the phenomena? And then using those questions to help drive where your next investigation is going to go. And this is where the core ideas come in. Our physical, our life, and our earth are all going to be related to whatever phenomena we choose for the engage. For explain, this is where students really have the opportunity to dive into those science and engineering practices, and this is where the educator can start layering on that academic language. We're not going to front load vocabulary in the engage stage. Rather, we have the students engage in the exploration, and then when it comes to the explain, the educator layers on the academic language and introduces it through this stage. And the elaborate phase is where students really extend their conceptual understanding of those science and engineering practices, but this is also where the educator can ask the students to think through the lens of a cross-cutting concepts. Perhaps it's patterns, or energy and matter, or systems and system models. And then evaluate is really coming to terms with what have we figured out so far, and allows the teachers to really look at student progress towards figuring out that phenomena. And so what does this look like when we're actually in the classroom working with students? And so there's this great document that does a side-by-side comparison of what does the teacher do during each of these phases, and then what does the student do? And for this webinar today, we're just going to focus on the student side. And what I'd like you to think about as you scan through this right side of the document is, where are the students able to put some of that information into a notebook? So as I go through the engage, what from the engage could they actually enter into a notebook? So think through each stage, and then choose one stage and report in the chat box what's something a student can really put into a notebook for that stage. So as you read, think of one of these phases and what's something a student can put into their notebook. Definitely new questions, absolutely. Once we figured something out, what questions do we still have? Excellent. Okay, if there's no other thoughts, we have elaborate, students sharing ideas. Yeah, definitely. Thank you. And I will provide this document for you. And so let's move on. So here comes the part you've probably been waiting for is, how do we take these 5 E's and really structure a notebook so that we're hitting every single one of the 5 E's? And so this is something that I created a few years ago that I tend to just kind of tweak as I learn more things. And this is something I used in the classroom for a very long time. And so I'm going to just define the term component for you. So a component is literally what the students put into their notebook. And you can see that I had several different components to put in a notebook. And so I'm going to walk you through each one of these, but then I will show you some examples after this, so just hang tight. So for the first, if we take a look at the engage, I always had the students start with the title. What's the actual title of the lesson or the beginning of the lesson? So for example, it could be called Reflecting Light or Heating Earth's Surfaces or whatever you come up with. They record the date that the learning sequence or lesson started, and then the driving question. What are we trying to figure out for the day? And that question is usually based on your anchoring phenomena you're working with. But you don't want to give away all the details in your question. You just want to give them enough to get them kind of hooked and ready for the phenomena. Then you have your background or getting ready. I've seen some people call it getting started or getting ready or background. And a long time ago, we used to call it pre-lab. I don't know how long everyone's teaching, but that was the thing when I was in college back in 2000 and who knows what, early 2000s. So the background or getting ready is really, this is where we engage students with that anchoring phenomena. We show them something. We get them to spark their curiosity and go, huh? What was that? And we start to really ask them to generate questions, and then we can use something called a driving question board, which is basically taking kids' questions and putting them into categories and asking them, okay, what do we think we should figure out first, second, or third, and prioritizing them. And so the color coding I have here, anything in blue is related to a science and engineering practice, and anything in red is related to an instructional strategy that is coincides with three-dimensional instruction. And so after you show them phenomena, they can do an I notice, I wonder T-chart about that phenomena, and that can go right in their notebook in what we call background or getting ready. So it's really, what do the students need to know before they start exploring? And so once you've got that foundation going, we move into the explore stage. And this is where I have three components: materials, safety, and data. Materials does not mean they're listing out the materials. Unless they are planning an investigation, then they need to write out their materials. However, if I already have the materials ready for them, what I have them do is check through each one of those materials and simply put a check mark next to the word materials in their notebook to say, yes, I checked, I have everything I need. Then I usually did safety, and this just means it's a point in our day where we have a conversation about how to be safe, and if everybody in the class agrees, I just put a check mark next to the word safety. Then we move on to data, and data is really where you spend the most of your time in the exploration phase. This is where they're engaging in all of those science and engineering practices. Maybe on one day you're gathering evidence. Maybe you're starting to draw an initial model, recording observations, using a graphic organizer, a table, a graph. Any of those tools when they start figuring something out and putting it into their notebook. That's what comes in the explore, and I called it data. As you move down, we have the explain phase, which in the notebook I called analysis. I've also seen other people call it explanation. This is where you come in as the teacher to facilitate the discussion on how do we actually analyze and interpret data that we collected in the explore phase. Then we begin to start constructing explanations and using the evidence to argue. We use graphic organizers like claim evidence reasoning, or strategies like the I2 strategy, which helps you think through graphing. And if you haven't seen that, definitely take a look at it sometime. Just Google it. Analogy mapping is a good tool to use to explain models, and you as the educator are the facilitator of this discussion and helping students really understand what they figured out at this point in time. When you get to elaborate, this is what we call building understanding or taking it further. I called it building understanding 1 year, and the next year I decided to call it take it further. And so this is where we use an analogous phenomena, where we take a similar situation that the students just figured out, but it's not the same scenario, and see if they can apply what they just learned to that new phenomena. They can also design additional investigations to push their thinking further, ask more questions, and this is where the cross-cutting concepts come in. Finally, in the evaluate stage, I literally called this the wrap-up, or as I got further into my three-dimensional learning, is we called it what did we figure out? We always kind of had a checkpoint of what did we figure out so far? And so you can use something like a summary table, which basically summarizes what they figured out and keeps a running record of it. You could give exit tickets, any formative or summative, quick checks, any of those kind of evaluative tools are really great to use in the evaluation stage. And so this is a lot of information, and I understand I just threw that all at you, but I'm going to show you an example. So this is an example from my class. I was working on a unit in climate and weather, and I decided to choose a phenomena about the melting ice at Glacier National Park. And so I started off with this video from National Geographic as my engage. After we watched that, I gave the students what's called an anticipation guide, and it really elicits students' initial ideas. They do a before, so you give them a few statements. They say whether they agree or disagree with it before they do the investigation, and then once you're done and you've figured some things out, you come back and report what you've learned by reviewing that and going to the after part. After that, here you can see this is an actual student notebook page where you can see the activity title, the date. We called it challenge question at the time instead of driving question. Then we had getting started, material safety, and then data. They were planning an investigation called Heating Earth Surfaces, where we wanted to investigate land versus water. So you can see down in the data section how she was just writing about, what are we doing? What's the purpose of this investigation? What are we trying to figure out? And so then we designed an experiment or an investigation between using water and sand and tracking the temperature over time. So here's our data table that went with it. And then we graphed our data and used the I2 strategy to really break it into when things got heated up and when they got cooled down, and just broke apart each piece of this data and started analyzing it together as a class and making notes on our graph. Then I gave them some analysis questions based on the data to see if they could really take that data and interpret it and explain what does that data actually tell us and how does that help us figure out the phenomena. Then the final thing was to use a graphic organizer for CER, claim, evidence, and that was my evaluation tool right there, is I really needed to see what they could figure out at that point in time. And so if you're kind of looking at, this is the setup for the notebook, this picture right here. I hope that gives you a little clue into how I did that. And so now that we've kind of seen it in practice, how do we really have success with science notebooks? Well, we have to make notebooking a routine. It has to be a constant practice in our learning sequences to make sure students are utilizing it and referencing it to help them figure out the phenomena. So one suggestion is to keep a teacher version of the notebook. Whatever you're asking the students to do, keep a version for yourself. I had 4 notebooks for 4 of my classes, so I knew where every class left off, and that way, if a kid, I had a notebook ready to go that person could use. Also, model how to use it. I took about a month or 2 at the beginning of every school year to really sit with them and show what goes into a notebook and what are the things I should put in a notebook. Then make sure you plan time in every science lesson and every day. When you're planning, think of this question. Ask yourself, what should the students enter in the notebook today? If I'm an Explore, what does that look like? Is it a data table? Is it a graphic organizer? If I'm in Evaluate, what does that look like? And so just really planning out what goes in the notebook every time you sit down to plan a sequence. Then, the best tool I can think of is to think aloud with your students as you're modeling how to use that notebook and saying, okay, so I'm thinking about this, I'm going to start writing my questions, and just really modeling how, scientists think and do their notebooks. Another useful tool is to show samples and make a notebook with the students as they do it. Use sentence starters and sentence frames. And this is the best idea ever that I came across in doing notebooks for 16 years. Entering additional sheets. And what I mean by that, I'm going to show you an exact example, is if you have some sort of student sheet that you want everybody to put in their notebook, but it's too big because it's on 8.5 by 11 paper, you can shrink it down to 75%, and you could fit 2 of them on a page. And I'll show you what this looks like in just a second. Then, if you get really good at notebooking, what I did in my last school is we had a common format throughout the whole school, from kindergarten all the way up to 8th grade. We were a K-8 school, and every science class was using a notebook using the same components. So what does taking a data sheet and shrinking it to 75% actually look like? Well, here's an example from energy. I took it, I shrunk it, I put 2 on a page, then you can just use half of this, cut it out, and then you can ask the students once they've completed it and used it to help them figure out to literally tape it into the notebook in the spine with one small piece of tape, and I'll show you what that looks like. Here's an example from one of my notebooks, and you can see they had a little recording daily weather, and where I circled is just one small piece of tape, and they tape it in so that the page can actually flip, and it actually becomes like you're adding additional pages into the notebook instead of gluing it onto a page and taking up all that space. And it's flippable. Here's another example. Let's use some pretty cool tape. And here's another example. So I shrink them down and I have tape in their toolboxes on their tables, and I just ask them to tape in, and that way they can have it forever and use it as a reference. And so let's do a little bit of reflecting and setting goals before we are done with this webinar. This figure, and I will give time for questions at the end just to let you know. This figure 2 is also from the author of that science notebook text that I showed you, and it really goes through how do I develop an insightful implementation of science notebooks. So let me blow it up real quick. And I want you to take a look and look at this from left to right. On the left side, we have mechanical use of notebooks versus, if you come to the right, insightful use of notebooks. So take 1 or 2 minutes and really read over this document, and then think of what are 2 things you are willing to commit to as a goal that you can do when you go back to your classroom with your students. And then put it in the chat box. Same setup is really helpful because then the expectation is there and they know what to do, so they feel empowered. Any other thoughts about how 2 top goals to implement notebooks insightfully? So are there any questions about implementing science notebooks or any of the things we talked about today? I'm happy to take some questions. If you don't have any more questions, you can feel free to exit, but I will definitely stick around if you have questions. Did I use a rubric to grade students on how their grades were weighted? That is an awesome question. I have used many different rubrics and many different strategies, and my favorite one is I actually never collected a notebook, not once, and I use this strategy called like a notebook check. And basically what you do is it was just an organization sort of assessment, and I was looking to see if they were, making sure that they had all the things in there that they needed in order to help them make sense of the science. So data tables, their questions, all the things I asked them to put in their notebooks. I would basically, every 3 activities I did, they knew a notebook check was coming. And so what I'm looking for is, do you have all of the components that I asked for that particular notebook entry? And I would write out the questions, and they'd have to go basically do a scavenger hunt in their notebook and find those answers. It was a quick check. It really allowed me to just check in their organization. I never graded them on content knowledge. It was more of an organizational side of things. And that way it really kept them accountable. So if they knew that they were going to be absent, or if they were absent, they knew I was going to be checking every 3 notebook entries. And so it really kept them, accountable, and they knew it was coming, and so they made sure to come and get the notebook from me or borrow another student's to get the notes. So I didn't actually grade the students on, it was more of a notebook check on how they were entering the components I asked them to enter. And I'm happy to show you an example if you shoot me an email. Okay, if there's no more questions, you can go ahead and exit. And again, just keep an eye out for 2 emails. And thank you all for coming.